Hi, my name is Gautam and I'm from CERIS, which is Solar Energy Research Institute of Singapore, and we are here to present a talk on webMathematica, how we are using it to deploy all our scientific simulation programs on the web, and we're very excited. Thank you.
Hi, my name is Rahul Jaiswal. I'm from the Solar Energy Research Institute of Singapore. Today I am going to present how we use webMathematica tool to create REST APIs, which are used as simulation tools in our PV community. So, good afternoon. This talk focuses on an ongoing project at our research institute, which is the development of an online simulation platform. Wolfram product Mathematica is used quite extensively in this project, specifically the webMathematica tool to create web services that are used as a backend to our online simulation platform. And this talk will talk on the both aspect of this development, basically the development of the web services and the software architecture behind the online simulation platform itself. So let me allow to give you an outline of this talk. I'll be giving you a background information of this overall project. Then I'll move on to explain the vision we had for this platform, the approach we took to achieve that vision, and how Mathematica exactly comes into picture. Then I'll move on to explain the API development methodologies and the various web services we have developed for the different use cases we have in our community. Then Gautam would be taking on this talk, and he will give you a detailed overview of the Excel Hetero web simulation platform itself, followed by a demo of how the website looks and feel for an end user. So the photovoltaic community is one of the major driving forces for the global spike in awareness towards the use of renewable energy. It has the highest installation capacity and the steepest learning curve across all the renewable energy sources. Still, the usability of a solar cell is bottlenecked by its efficiency and its cost factor. And a large volume of research in the PV community utilizes simulation programs and modeling tools to understand its material and physical properties. But this approach has some challenges associated with them. These simulation programs are basically written in a variety of different programming languages. There is no set standard to communicate between them, and they require a bit of training before one can start using them. Also, there is a lack of any type of centralized database in the PV community to which a researcher can upload their measurement data. The PV community is also lagging behind in exposure to modern computational concepts such as machine learning and data analytics that they can perform over the large data set they already have. Then there are expensive and complicated licensing mechanisms associated with the use of these simulation programs, which provides a hindrance to use of them for a researcher or a PhD student. Now, this problem can be solved easily if these features, these simulation program, data upload capability, and data analytic models are available through a single platform. The Solar Energy Research Institute of Singapore is working on such a project which brings together these features in a cohesive manner. CERIS is the National Institute for Solar Energy Research in Singapore, and for the past decade we have developed a lot of simulation programs, and we also have access to many characterization and processing tools in our clean rooms. So in essence, we have a data set which is composed of both real measurements as well as simulation data set. So the platform I just talked before, which brings together these features, let's suppose it's a web-based platform. Then it makes even more easier for a researcher to do simulation tasks online as well as to upload their data to a centralized database. So with this motivation, the development of our online web simulation platform was started. And to understand the project, you have to consider its 4 main layers. First is the user interface, which is the only part accessible to the end user, through which they can do simulation tasks, they can upload measurements, or they can provide inputs for these simulation or measurement programs. Then there are microservices dedicated for performing individual tasks, and that's where webMathematica comes into picture, because it allows us to develop these kind of microservices for doing specific simulations or creating programs to upload data or to do data analytics also with the modern machine learning capabilities in the latest Mathematica version. Also, we have a centralized database to which a user can upload measurement data coming from a processing or a characterization tool, and this database is further divided into process database, measurement database, and solar cell architecture database. The last phase of the project would then be to deploy machine learning tools and data analytic models over the large data set collected through such an interface. So for this interface, the vision we had was it should be easy to access. The development for this platform should be easy for developers who want to put their web services on this platform. The end user shouldn't access the source code of any individual simulation programs. And also, as it's a website, the computational resources allocated for a single execution should be kept minimalistic. And we are in a learning curve, so the development methodology should be flexible enough for future amendments. So the approach we took to achieve this kind of vision was to convert all our use cases to individual application programming interfaces. The reason being, these APIs provide us on-demand computation, and they are individual endpoints, so they can be configured to run in a parallel or a pipelining manner. Example where pipelining concept is useful in our context is, let's suppose user wants to upload the data from a characterization tool doing current voltage profiling of a solar cell. They can use an API number 1, which just converts this data to a standard JSON object that can be saved in a database very easily, or can be fed into another API which is tasked to do some post-processing on this data to get some additional parameter useful in our context. So I've talked about the vision we had, the approach we took to achieve this vision. Now, how exactly Mathematica comes into picture? So using webMathematica, I can create web services that I've just talked now, these APIs. Also, results from webMathematica can be returned in format of a string that is in turn can be structured as a JSON object, which can be understood by your online simulation platform to be stored in a database or to be post-processed on by another further API. Also, many simulation programs were already developed using Mathematica at our research institute, so it was quite easy to convert directly them to a web service. In this section, I'm going to talk about the API development methodologies and the various web services we have developed so far. So all our APIs are kept in a Ceres Web Mathematica server, and our simulation server connects to these APIs through the Tomcat servlet engine. So the request URL from our simulation platform contains the query variables, which are basically the inputs for any simulation program or data upload program. And the results are structured in a standard JSON object, which is in turn very standard for different type of measurements and simulation. So how an API endpoint looks on a browser is like this. So basically this one is tasked to just upload current voltage data coming from a characterization tool. It needs some inputs such as the path of the file generated from the characterization tool, let's suppose an Excel file, and some more inputs. So just to save time, I've filled in these inputs. So this path can be a network path or a local path, and that's how Accelehetero can consume these kind of APIs. So once I click submit, I get a JSON which contains the same current voltage data, but now in a very structured manner, so that it can be saved in a database or can be operated on further. Also, the lot of inputs you see here are basically classified into two parts. One which is provided by the simulation platform itself, like user ID or execution time, and others like specific to a simulation program or data upload program, like in this case, the thickness of the wafer of which current voltage profiling has been done. So back to our program. The various APIs we classify on the basis of the task that they do. So one such class of APIs are those which are used to just upload data from individual characterization and processing tool, and they are fairly simple to develop because all they do is to just upload the data. Exception being the upload of images, photoluminescence and electroluminescence images. These images provided by our imaging tool are in a raw TIFF format, and they need certain further post-processing to be calibrated to a color scale. And using Mathematica, we can allow an user to choose on a scale a minimum and maximum PL count values through which they can do some introspection of the image to find out certain traits in a PL image. So in case of a PL image, they can find out measurement artifacts like these coil rings, or in case of an electroluminescence image, they can find out characteristics like a broken finger. So these are things that are really helpful for a researcher in a PV community. So this was the class of API which is tasked to do just upload of data. There's another class of API which is tasked to which is tasked for simulations, and we have a lot of these kind of APIs. Some of them are developed using Mathematica notebooks. Some of them uses desktop simulation programs. Some of them uses models which are written in Centaurus design environment or Synopsys design environment. And in the PV community, people still use Excel-based calculators. So we wanted to have that capability also, that people can, without downloading the actual Excel sheet, they can connect to it virtually using webMathematica and do some macro-based calculations. So the simplest one is the one which is developed in Mathematica notebook. A researcher at our research institute just follows certain rules and syntaxes that we provide in internal wiki, and they convert their Mathematica notebook directly to a web service that is ready to be integrated on our simulation platform. Then there are desktop simulation programs. These are executable Windows programs that we wanted to have an access through web services. So the methodology here is to run these command line executable programs through webMathematica, where the inputs for these simulation programs are provided by the user and mapped on to the inputs of these command line programs through webMathematica, and the results are then rendered back in a JSON format, which makes it easy to be saved on a database as well as to be shown to the user in format of a table or a graph. So already we have converted many established simulation program in the PV community like PC1D, Gridler, and Coca. Again, there are many models which are computationally expensive and are kept on a discrete server, like many device and process simulation programs are written in Synopsys design environment, and we wanted to have the capability to run these simulations through webMathematica web services. So the methodology here is to map in the inputs from the user to a pre-written shell script and to send this shell script to the CentOS server through SSH protocol. Once the execution is done on the CentOS server, the results are fetched back to our webMathematica server and can be then rendered in format of a JSON to be saved in a database or shown to the user. The last case of simulation APIs are those which basically opens an Excel sheet virtually using Mathematica link for Excel library and paste the data on which computation has to be done on this virtually opened Excel sheet. Then we have a Visual Basic code written in that Excel sheet which watches a particular cell or column to be filled, and then it initiates the macro through which computation has to be done. Once the computation is done, the results are fetched back to webMathematica and can be then shown to the user. So the last phase of the project, as I have talked before, was to do some data analytics over the data we can collect by deploying such kind of APIs. So we are yet not at that stage. We'll be launching the website in 6 more months. But just as a proof of concept, we wanted to test how good our Mathematica's built-in machine learning models and prediction tools, and whether they can be useful in the present scene only. So we used a simulation API, which is tasked to do boron tube diffusion process. So in the PV community, it is understood, but you can consider it as a black box where the inputs are the process conditions that are maintained inside this tube, and the output is a diffusion profile which can be characterized by these two parameters. So we wanted to check that whether Mathematica can build us a prediction model where we just provide the desired surface concentration and Johnson depth for a diffusion profile, and whether it can predict the process condition that can lead us to such kind of diffusion profile. So the first step was to create a training database. We ran this simulation program in a batch manner by statistically varying these input process parameters. So we were left with around 4,000 points. That's a quite small number of data points, but still it was a proof of concept. And the parameters that we were really interested in were the 6 process parameters and the 2 output characteristics. To keep things even more simple, we used the dimensionality reduction method in Mathematica to reduce this 6 process parameter to 1 dimension, so that in our prediction model, we were left with 3 parameters only to deal with. Now with the prediction model ready, we can ask it that I want a Johnson depth of 0.45 microns and a surface concentration of 1.5 E19 in my diffusion profile on my solar cell. What should be the process condition that should be maintained in the boron tube chamber? So it will return us with the reduced set of parameter, which we can expand it back to the original 6 process parameter using the same function as we did for reducing them. Now to check how good our prediction was, we fed these predicted parameters back into the original simulation program and did a comparison between the desired values and the one obtained through the prediction. So in this graph, you basically see on the x-axis the depth points in the wafer, and on the y-axis you see concentration on those depth points. So in essence, I asked it that I want a 0.45 micron of Johnson depth, but through prediction I got actually around 0.52 microns. But this goes on to so that we used only the synthetic data, but still the accuracy is quite good. And with real data coming soon with the launch of this website, we may be able to do some good prediction using Mathematica as well as using Python-based models. And this is something which can be really useful in the industrial as well as for academia use cases. So with this one, I'll wrap up my talk, and Gautam will explain how the X-Solar Hetero web simulation platform consumes these kind of APIs for an end user to deal with.
Okay, so great. So we just saw that Rahul told about all these simulation programs, all these upload programs, post-processing programs, they can be converted back into RESTful web services. So now we needed to understand that, so we'll talk about web-based platform which we are building, and the main features of this is basically 4 main features. The very first thing is providing a secure access, authentication, authorization, role-based access. Second thing is dynamic API management for all externally hosted web services, so which in this case is all the webMathematica APIs, queuing mechanism, all sort of stuff. Second, the third one is basically access to all the dynamic and expert database. So this is generated by all the research scientists, research fellows, PhDs, and all sort of other people in the photovoltaic context, material database, architecture database, measurement database, process database. And the last point is basically create and provide access to all the big data for training machine learning models in the future, and then putting them back as another RESTful API in the system. So these are the kind of different features which makes Xsolar Hetero a little bit more interesting. Now, to understand what is the software architecture, the first thing we need to understand is who are the users of the software. So we identified 3 different user types. The very first one is basically the expert database creators. So the scientists, researchers, PhDs, and so on. So they will put all their knowledge information in the system. The second guys will be the developers. Developers are like Rahul. They really are passionate about understanding how machines work, how simulation programs work on top of an expert database, so they can upload all their programs back. The third people are those people which are called researchers. These are basically process engineers working in clean rooms and factories in different environments. They do not understand much about how these programs work, because what they're really interested in uploading the measurement, getting the right graphs, and use them to compare and see how the progress is going on. So let's just understand from the mass user perspective, which is the researchers, how will they use the system? So you can see from the bottom, it's you can use the web browser, they can go through the firewall, use the authentication, do authorization, select the tool they're working on, and then select the architecture. The system will know which program they're talking about, which operation they're talking about, and then we'll go and query the webMathematica RESTful, the management system, and figure out, okay, this is the API we're talking about. We'll go and talk to it, queue it, get the response back, and handle it and show it to the researcher. And what the researcher is now going to see is the graph which they're interested in. So when they think this is the right kind of visualization of their measurements or the simulation program, they can just save back in the personalized measurement database, which is a kind of a value addition to their personalized database. Okay, so before we talk about the researcher panel, we need to understand what we have uploaded back in the last 3 years. So we've been developing this project for about 3 years now, and what we have added is 19 materials, 67 solar cell architectures, 10 different measurement schemas, a bunch of programs, basically 5 upload measurement RESTful APIs, 5 simulation RESTful APIs, about 3 post-processing programs which work on top of the upload and the simulation program, and then 1 machine learning model just as a proof of concept that, okay, we can deploy this and we can go on. But then what we aim to go is create a researcher interface where basically all this deployed expert knowledge, all these different APIs which does processing and simulation, give access to the guys in the clean rooms or in the factory environments. So how do we do this? We create a researcher interface, which is a very straightforward, simple interface, as simple as like 5 clicks and your all data is in, and then you can simply use it for all your performance metrics and other stuff. So yes, we are still in development. We are still doing this test internally inside our company environment. So about next 6 months, we'll be done with the beta test, and we'll move out to try it out for different institutes, and then maybe even to the industry in the future. Okay, so I have 2 demonstrations. The very first demonstration is basically integration of your API on the X-Hetero. So basically, if you were a developer like Rahul, then you wanted to upload your program back to X-Hetero, how would you do this? The second demonstration is more like a live demo, where I will say that, okay, I've uploaded certain program onto the X-Hetero, and then I'm a researcher, and I want to consume this on my day-to-day use case. And then we'll talk about a little bit of conclusion. So before we go, before I go to the first demo, I would like to show you the expert database we are having in the system. So these are all the 19 materials we have in the system. All these materials are all dynamic. They can be scaled. Yes, we do in context of solar at the moment, but this is all material science. You can add it to any sort of field you want. So that's the message here. Then there were engineers and research fellows which took these materials and built solar cell architectures on top of it, like how a solar cell is made, different layers of materials, and then what are the properties of each material to fit in so that they can work together to create a nice optimized solar cell. So this is, you can see there's about 67 of these different solar cells which we do inside our institute. So these are like a bunch of them. So there's about 100 more which are coming in the next few months. And then the last step is, once we have uploaded the materials, the architectures, the next step is adding a program as a developer. So I will go through the process of how to upload it, but these are generally all the programs in the system. So there's an IV, diffusion profile, spectral response. You can see all sort of standardized solar context measurement tools, also the simulation programs, the Quokka, PC1D, and then all post-processing programs, and even the machine learning program as well. So without further ado, a demonstration on the video. So in this, what you can see is, on the left-hand side, this is the same API, webMathematica API, which is locally there on my system. And what I'm trying to do is, I'm trying to basically upload it back to Xsolar Hetero. So I'm going to a little bit fast forward it. I'm going to show you, I'll just go to the Xsolar Hetero. Yeah. Okay, I'll go to the Xsolar Hetero. I will fill up as simple as a form, and what I will do is I will put all the information of my webMathematica API endpoint, where it is hosted, the version number, the details, the name, and all the other information. Basically, all the input and the output information which I expect from this webMathematica API. So my Xhetero platform is going to curate, do a quality control check on the input and the output, and will ensure, okay, this is correct, this is in context of my solar outcome, and this is something which is standardized. Of course, I can add collaborators which can later on access this information. And then, okay, then I'm going to go a little bit more fast here. Okay, so I'm going to add, yeah, okay, maybe I'll show you. Okay, then I'm going to add an operation. So this operation is basically what I want to do on this measurement. So for example, here I'm trying to do an IV upload, and inside I want to get the current voltage profile. So I will add all the input parameters, and then what this will do is, this will basically call the API on the webMathematica endpoint. Okay, and then we get a graph. Okay, this getting a graph means the quality check has passed, and you can save this rule back. So what we have got here is basically all a quality version of our API. So our API is working. We can add it back to the system. So yeah, so you can see the expected graph is basically something like this. So if we get a graph like that, we are actually good to go. The second demo I'm going to do, a quick demo, is basically use the website as a researcher now, not as a developer, and try to use this uploaded information and upload my daily measurements. So what I'm going to do is I'm going to choose, go to upload button. I will choose my tool, which is a Wavelabs. This is a specific kind of a tool which we added. It will go and check the cell. It knows which architecture I'm talking about, so it will show me a photo of that. So I know, okay, this is what I'm talking about. I will just select my file, and what I'll do is I'll just simply upload. And then once the system has been uploaded, it has been added to my queue. But now I do not know it's correct or wrong. So the next step for me is basically to confirm this measurement. So what I'll do is I click this button. And what has happened here is, in real time, the system knew which webMathematica API to call. It threw back me the graph, which is kind of correct now. So what I can do is, now I can just confirm this measurement. And this is now saved into my personalized database. Now this is very valuable to process engineers and the people who work in the factories, because what they can do is, now they have their own personalized database which they can curate, and they can simply compare, they can know their progress, and all sort of different stuff in an environment inside a factory. And moreover, they can also use it to create machine learning data, training data for your machine learning models. So that's the direction we are trying to go into. So yeah, so what is the conclusion we have? The conclusion we have is we have obtained the capability of uploading measurements using RESTful web services. So we support all the standardized characterization tools at the moment inside the Solar context, capability to execute simulation programs as RESTful web services. And then here we support command line tools, Wolfram-based tools, server-based tools, Excel-based calculators. And the capability to manage these RESTful API services in a photovoltaic context. And then also have the capability to integrate machine learning models on top of it. So at some point, we will have a lot of data, and we can use all the awesomeness of Mathematica to build machine learning models on top of it. And of course, now we are in the state of building this interface for upload measurements, simulation measurements, and soon we'll have the machine learning model. So that's pretty much it from our side. Thank you very much.